Hello and welcome back to PC Retro Programmer. Today's video is about the binary and hexadecimal numbering systems, and we'll briefly touch on binary coded decimal as well. Now you probably know that us humans work with decimal numbering, which means that we have 10 digits to deal with, 0 through 9, and that most likely this arose historically because on average we have 10 fingers. Which sometimes we also refer to as digits as it happens. Now, of course, computers don't have fingers, but they do have logic states, and so you probably also know that on a binary computer there are two logic states, which electronically are a low and a high level, and these correspond to the digits 0 and 1. So computers want to represent numbers using just two digits, 0 and 1, instead of the 10 digits that we normally use. And so this leads to the binary numbering system. Now you've probably also heard the term bit, for example an 8-bit or a 16-bit computer. And it turns out that bit is just an abbreviation of binary digit. So a binary digit or a bit can be either a 0 or a 1. Now I probably should mention just in passing as an aside that it's a little bit more complicated than this in practice. It turns out that tri-state logic is not that uncommon on computers, but at least from a programming point of view we never need to worry about this. Everything's always presented to us in binary. But you might wonder, why is it that we need to deal with binary numbers at all? After all, when I execute a program, which certainly is stored on disk as a big long string of zeros and ones, and it's encoded using something called machine language, which is the native language of the CPU. It's the native language of the machine. We don't actually write the program using big long strings of zeros and ones. We'd certainly go cross-eyed if we tried. Instead, what we do is we write in a much more human-readable form called assembly language. Now, there's a very close correspondence between the two. Each machine code instruction that the CPU can execute corresponds one-to-one with an assembly language instruction that we can actually read and write much more easily. So why don't we have the program, which is called an assembler, that converts between our assembly language program down to the machine language that the machine can understand? Why don't we have that also convert all of our decimal numbers down into the corresponding binary numbers? And that way we'd never need to see a binary number. Well, you certainly can do that. Any decent assembler will actually allow you to enter all numbers in decimal format, the format that you're most familiar with. But it turns out that there's another reason why you want to be able to deal with binary, and that has to do with the actual assembly language instructions themselves. A CPU is able to deal with binary numbers much more efficiently than with decimal numbers. And so if you really want to get the greatest possible efficiency out of your program, which, let's face it, you're probably wanting to do if you're writing in assembly language, you really need to understand the world from the computer's point of view, from the binary point of view. So let me give you a very simple example of this. In decimal, if we want to multiply by 10, it's very simple for a human being to do. We simply shift everything left by one digit and just tack a 0 on the end. So multiplication by 10 in decimal is trivial. It's just a left shift by one digit. Now, unfortunately, on a binary computer, multiplication by 10 is actually very inefficient. If you do a left shift by one digit on a binary computer, this actually multiplies the number by 2, not by 10. So that's the thing that the computer can do efficiently. And there is actually a left shift assembly language instruction which will very efficiently multiply numbers by 2. And so this is why you might want to know about the binary number system, because you need to understand what is going to be very, very fast. And there's a whole pile of tricks, collectively referred to as bit twiddling tricks, which you can use to do all sorts of operations very, very rapidly on a binary computer, some of which would even be difficult to do in decimal. So that's the main reason that we use binary numbers, but as it turns out, writing strings of zeros and ones can still be complicated for a human being, and it's very easy to lose track. And so there is a compromise that we can use, and that is the hexadecimal numbering system. So in hexadecimal you actually have 16 digits. They're 0 through 9 and then A through F, so a total of 16 different digits. And it turns out there's a very nice correspondence between hexadecimal digits and binary digits. In fact, each hexadecimal digit corresponds to precisely 4 binary digits. And unfortunately, there's no similar correspondence between decimal digits and binary digits or bits. So this is why we typically find a lot of hexadecimal numbers in assembly language programs. They're a bit easier to read for us humans, since we don't go cross-eyed looking at all the zeros and ones, and we have 16 digits to play with. But it still corresponds in a very natural way to the actual binary numbers that the computer's working with. And so this allows us to think in binary whilst writing in a more convenient form. So that's the second topic for today, hexadecimal. But there's one other topic that I mentioned, and that is binary coded decimal. And this is a little bit of a hack. It's actually used pretty commonly on pocket calculators. And there are also other applications of binary coded decimal, for example, financial arithmetic, and I'll explain why that is later. But it's basically just a hack to allow computers to work with decimal instead of binary. They still have to encode everything with zeros and ones ultimately, but there's just a representation for each of our 10 digits using zeros and ones. It's much less efficient in practice, but on a pocket calculator, for example, you don't tend to care that much about performance. And certainly if you're doing financial arithmetic, you can get much more accurate results for reasons that I will discuss a little bit later. So that's the third topic for today. So let's start off by discussing the binary and hexadecimal numbering systems and give some examples of conversions to and from the ordinary decimal numbering that we're used to. Now, as I mentioned, in the binary number system we have just 2 digits, 0 and 1. And so what I've drawn here is a little representation of 8 binary digits. I haven't actually written any digits in here, but each of these spaces could have just one binary digit or one bit in it. So it could be either a 0 or it could be a 1. And the reason that I chose to draw 8 of these is because 8 binary digits, 8 bits, is a byte on a computer. And on an 8-bit computer, internally inside the CPU, you would have little storage locations called registers, which can hold 8 binary digits, 8 bits. And so in those registers, you can represent numbers that can be written in the binary number system using 8 binary digits, each of which has to be either 0 or 1. Now, the way it works is that instead of having a move to the left by one column being multiplication by 10, which is what we have in decimal, so this would be the ones column and the tens column and the hundreds column, the thousands column and so on. In binary, when we move left one column, we multiply by 2. So this is the ones column, the twos column, the fours column, the eights column, and so on. And it turns out that we can represent all the numbers this way using just 2 digits. Now, of course, if you want bigger numbers, you can do that if you want. You can have a 256 column and a 512 column and so on. Just like with decimal, you just keep adding digits if you want bigger numbers. But if you want to represent them inside the CPU in a register, you'd need maybe a 16-bit CPU if you wanted to have 16-bit numbers, and you could have a 32-bit or a 64-bit CPU. And then if you still run out of space, well, you can just string a whole pile of bytes together, and it's exactly like decimal, you just add more digits if you want a bigger number. Now in hexadecimal, we have 16 digits, and we write them 0 through 9, and then we just use A through F. So that gives us a total of 16 different digits. So each of these locations would have one of these in it. And moving one column to the left in hexadecimal multiplies by 16. So this is the 1s column, the 16s column, the 256s column, the 4096s column, and so on. And the reason that I only drew 2 of these here is because a byte in hexadecimal is just 2 hexadecimal digits. In fact, each hexadecimal digit corresponds to exactly 4 binary digits, 4 bits. So this digit here would correspond to all 4 of these, and this digit here to all 4 of these. And we'll talk about exactly what that correspondence is in a moment. Now you might wonder, how do we represent that we're writing in the binary number system as opposed to, say, decimal or in the hexadecimal system? Now in books, this is usually done with a little subscript. So in a binary number, you would normally have a string of noughts and ones, and then you would follow it with a subscript B or perhaps a subscript 2. In hexadecimal, again in books, you would tend to find little subscript H or a 16, especially in expensive books, I find. Now on a computer, that's not very convenient, since writing subscripts is a little bit messy. And so there are other ways of denoting that you're in either the binary system, the hexadecimal system, or the decimal system. And that's particularly important if you're writing an assembly language program. You need to tell the assembler whether your number is binary, hexadecimal, or decimal. And so we'll look at those as well. But first of all, let's just start off with some examples of converting some decimal numbers into the binary number system and into the hexadecimal system. So the first thing that we're going to do is write a decimal number in binary and then in hexadecimal. So I just picked a random number to do this with, so I chose 71. And basically what we need to do to write it in binary is to figure out which columns we need to put 1s in. And you remember in binary that the columns correspond to powers of 2. So you have the 1s column, the 2s column, the 4s column, 8, 16, 32, 64, 128. And so basically what we have to do is write 71 as a sum of distinct powers of 2. So they all have to be different, and they have to be powers of 2. And there's only one way of doing this. Every number has exactly one way that it can be written in binary. And so the way we do it is we start off with the largest power of 2 that we could take away from 71. And so that's 64. I couldn't go up to the next power of 2, that'd be 128. That'd be too large. I couldn't take that away without it becoming negative. So 64 is the largest power of 2. And when I take this away, I'm left with 7. So now I have to write 7 as a sum of powers of 2. And the largest one I can take away from 7 is 4. I couldn't go to 8, that'd be too big. So 4. And when I take that away from 7, I'm left with 3. And I think you can see that this goes all the way through. 3 can be written as 2 plus 1. And so this tells us precisely which columns we need 1s in. We need a 1 in the 64s column, a 1 in the 4s column, a 1 in the 2s, and a 1 in the 1s column. And that's precisely what we've written out here. So let's just check we got this right. 1s, 2s, 4s, 8s, 16s, 32s, 64s. Yes, so we got the right one. Now notice we've got a leading 0 here. Of course, just like decimal, you can leave off any leading zeros. You don't need to put those in, but I'm thinking of this as an 8-bit value that might be in an 8-bit register, and so it's not uncommon to see leading zeros in binary numbers. So now let's write this in hexadecimal. And of course the way that we do that is to go from the binary number rather than the decimal number. You can go directly, but it's just a little bit more fiddling around. So what you do is you break the binary number up into two sets of 4 bits. So this would be the first set of 4 bits, and if we thought of this as the 1s, 2s and 4s column, then this set of 4 bits is the number 4, and I can write that in hexadecimal using the digit 4. And for this set of 4 bits, I have 1 plus 2 plus 4, which is 7, and so I just write the digit 7 in hexadecimal. Now, if this had been a 1 here instead of a 0, we would have had 8 plus 4 when we did these 4 bits. And 8 plus 4 is 12. And so how do you write 12 in hexadecimal? Well, it's just the digit C. Remember, we use digits 0 through 9, and then we use letters A through F. So 12, 8 plus 4, would correspond to the digit C. So it would be C7 in hexadecimal in that case. Now, as I explained, these fancy ways of writing things are usually found in books, but this is difficult to do on a computer because of these subscripts. So we have 2 other ways of writing hexadecimal numbers on computers. So this one is typically found in assembly language, and this one is more typical in a language like C. So basically this is still telling you that it's a 2-digit hexadecimal number. The little h is for hexadecimal, and I put a leading 0 here. Now, you don't actually need the leading 0 in this particular case, and the reason for that is that the first digit is between 0 and 9. So if it had been a letter, then the assembler could get confused. It might think that this is just a symbol or a label or something like that. So numbers have to start with a digit from 0 through 9, and so to make that happen you put a leading 0 out the front. But as I said, you don't really need it here because the first digit was already from 0 to 9. But I put them in just out of force of habit. I mean, you need them when the first digit is a letter, A through F. And so once you've done that a certain number of times, you just give up and you say, I'll just always put the leading 0 in. So it's not uncommon at all to find a leading 0 on hexadecimal numbers for this reason. Now, the other way of writing it is like this. This is 0x47. This 0x at the front is a way of telling the compiler that this is a hexadecimal number. It just has 2 digits, same as all the other representations here, and the digits are 4, 7. So these are the 2 ways that we can write hexadecimal numbers on a computer. Now, if we're going back the other way, this is trivial, of course. A 4 in binary is just 0100, and 7 is 0111. And if I wanted to go from here to decimal, well, it's 64 plus 4 plus 2 plus 1, which is 71. So it's actually quite easy to go back the other way as well. The other thing that we should learn how to do is to count in binary, and I'm not going to go all the way up to 8-bit numbers here, so I've just written out all the 4-bit binary numbers here in 2 columns. So we'll start with 0. It's obviously just 0, 0, 0, 0. I didn't bother putting the little subscripts in, but I could have put little 2's in here if I wanted to. And the rule is very simple. What we do is we replace a 0 in this column with a 1 to add 1. You can see that's always going to work. This is going to add an extra 1 to the number. Now, if we already have a 1 in this column, what we do is we replace all of the 1's that are in a row here. We replace them with 0's, and then we put a 1 in the next column. So let's take another example. Let's take this one here. There's 2 1's in a row here, starting on the right-hand side. We replace them with 0's, and we put a 1 in the next column. Of course, this one already had a 1, so we don't change that. So that's the rule. Basically, if there's a 0 here, it becomes a 1. If there's a string of 1's on the right-hand side, you replace them all with 0's and put a 1 in the next column. That's it. And so that's how you count in binary. So these are the numbers 0 through 15. In fact, you can actually see that all of these numbers here are exactly the same as these numbers here, except that there's a 1 in this leftmost column. And that's because all of these are 8 more than all of these. For example, 0 plus 8 is 8, and of course 1 in the 8's column is 8. 1 plus 8 is 9, that's 8 plus 1. 1 in the 2's column here, that will become 8 plus 2 over here. So this is 10, and so on. So that's how we count in binary. Now the final topic that I want to deal with is binary coded decimal, or BCD for short. And as I mentioned, there's just a handful of instructions on the 8086 and 8088 that actually do binary coded decimal. And as it turns out, there's a couple of peripherals as well that have some registers that can be programmed in binary coded decimal format. But it's still overall very rare. It's not something that we need to use often in assembly language. And in fact, the main applications for this are for pocket calculators, which sometimes even represent numbers natively in binary coded decimal instead of binary, and also some financial applications, which I'll talk about. So basically, the way binary coded decimal works is you take a decimal number that you want to write, and you first represent it in hexadecimal just by taking the exact same digits. So I only use the digits 0 through 9 here. I just ignore the fact that there are digits A through F. So of course these two values are not equal. That's why I didn't write an equal sign here. This is a code, a representation for this value. One that I can read off the digits, the decimal digits, very easily. I can see that this is the value 12.79, even though it's written in hex. And what you do from here to get to binary coded decimal is you just use the ordinary rule for writing this hexadecimal value as a binary value. So 1 becomes 0001, 2 0010, 7 0111, and 9 1001. And so even for a human being, it's easy to read off what this value is in decimal. It's 1279. So why would you do this? Well, it turns out that there are some values that are very difficult to represent exactly in binary. So just think for a moment about actual binary values, not binary coded decimal, but actual binary values here. The way things work when you have a binary point here, this would be a decimal point, so we call this a binary point. The way they work is that you have fractional powers of 2 on this side of the decimal point. So this would be the 1/2 column, the 1/4 column, 1/8, 1/16, 1/32, 1/64, and so on. So any number that can be represented exactly as a sum of these fractional powers of 2 can be written easily in binary. But just in the same way that it's very difficult to write a third in decimal, you'd need 0.33333 on forever, you'd need infinitely many digits. So if you use actual binary numbers, it's very difficult to write some decimal numbers exactly in binary. You need infinitely many digits in the binary side, even though you don't need infinitely many on the decimal side. Now this is only a problem for the fractional part. Obviously the integer part, we know how to write all integers in binary exactly, but the fractional part it's a little bit different. So of course binary coded decimal gets around this by writing the original decimal value in a way that can be represented exactly. So here I have the digits 1, 2, 7, 9. So this value is exactly representable in this binary coded decimal format. And this is important for financial applications. You can imagine if these were dollars and cents, you don't want to use some slightly incorrect value once you switch over to strings of zeros and ones. You don't want to just cut it off after 8 bits because that's all you've got space for in your computer and just lose whatever it is on the end here. You really want to be able to represent exactly the value 12.79. And in binary, you just can't represent every decimal value exactly in a finite number of bits. So this is why binary coded decimal is much more convenient. The only real problem with it, of course, is that it's just very inefficient. The instructions for doing arithmetic with this representation are pretty horribly complex. And so a lot of pocket calculators are quite slow if they use this natively. Some don't, and you'll find, for example, if you divide a value by 5 and then multiply by 5, you don't get the same thing back again. And that's because it really represented it as a binary value internally, and of course it only did it to finite precision, and so when you multiplied back again, you didn't quite get the same thing back. So there are actually two different versions of binary coded decimal. There's a packed representation and an unpacked one. So we've seen the packed one here, and in the unpacked one, it's basically the same idea. You just have fewer digits. So the value 12, for example, would be written 01, 02. You just put zeros between the digits when you go over to the hexadecimal side. And so this would become 0102. So this unpacked format has some advantages with certain arithmetic operations. Anyway, that is binary coded decimal, and as I said, it's nothing that we have to really work with on a regular basis. It's a very rare thing that we actually use binary coded decimal in practice.